class, how's it going? In this video we're going to do the real basic calculations for a two-sample t-test. A two-sample t-test is a test where you're drawing two samples from a population. A quick aside, the Atomic Learning tutorial for this two-sample t-test that you may have found, the narrator talks about the samples taken coming from different populations. That's not accurate. In this course, just go ahead and think about the samples that you're getting are from the same population. So I'll give an example here to explain what I mean. In this data scenario, I've got tomatoes growing in my backyard, and I want to see if a plant food that I bought actually works. So I separate the tomatoes. I have one group that I don't treat with the plant food. I have a group that I treat with the plant food. Now everything else with these tomatoes is the same sunlight, same level of gardening. They're in exactly the same place. The only thing different is the plant food. So after several weeks of growing, I go ahead and I harvest the tomatoes, and I take 20 at random from my untreated tomato patch, and I take 20 at random from my treated tomato patch. So I've got two samples, an untreated sample, a treated sample, and my treatment is the plant food. These do come from the same population because my population I'm concerned about is tomatoes. I want to see if this plant food would work on all tomatoes. I'm not a botanist, so I don't know if there's different species of tomatoes. I'm just talking about red tomatoes that a dude like me, I guess, would grow in his yard. So I've got 20 of each here, 20 untreated, 20 treated. There's my data arrayed in Excel, 2 columns. Should look familiar. I calculated means for my untreated group. I've got 27.8 as the mean. I calculated a standard deviation of 9.96. For the treated group, I have 32 as the mean, and I've got a standard deviation of 7.79. All right, so that's the basic summary statistics. And I want to run a two-sample t-test because I want to see if my observed difference between the means is big enough that I would conclude that I think this treatment works. I think this plant food actually makes the tomatoes bigger. Now, when you're running a t-test, you never work in an ironclad certainty. Ironclad certainties are pretty rare in research, and they involve double-blind studies, and that's not really the design we have here. What we're doing is we're taking two samples, and then based on what happens with those samples and our treatment, we're going to estimate what that means for the larger population of tomatoes. And to do that, the t-test is the test of choice. I'm going to run a two-sample t-test. Before I begin the test, I'm looking at these means and I'm thinking, okay, there's a difference. I mean, 32 is bigger than 28. But is it really big enough that I would conclude that I would put my faith in this plant food? All right, let's get into some of the t-test things you're going to need to do here. Some of the numbers you're going to need to generate and think about. The first one is degrees of freedom. Degree of freedom just means, how much leeway you have in the t-test itself. It's related to your sample size. If I have a big sample size, I don't need to see as big of a difference to conclude that something is significant, that my treatment works. If you can imagine that maybe I only had 10 tomatoes in each group, intuitively you can kind of think about that as you would want to see a big difference between these tomatoes with that small of a sample. With 20, okay, a smaller difference would potentially suffice to make me think, okay, this plant food worked. So that's what degrees of freedom mean. It's just that with a larger sample, you don't have to see as big of an observed mean difference to think that it's statistically significant, or for the t-test to generate a statistically significant test statistic for you. That's what degrees of freedom is. Alpha level is simply how stringent you make the test. In this course, we usually use 0.05. In certain situations, you'll see researchers go with 0.01. That's a very stringent test. Ours isn't going to be that stringent. But the beauty of a t-test is you can kind of just decide what you think is the appropriate alpha level given a research situation. And so alpha level really is just setting a 5% standard that I have to, for me to accept the null hypothesis, I'd be looking at p-values above 5%. For me to reject the null hypothesis, I would be looking at p-values numerically below 4%. Things that were likely, to happen less than 5% of the time by chance. That would indicate to me statistical significance. Okay, so that's all an alpha level is. It's just how stringent you're making your test. A p-value is really the big stat we're looking for in a t-test. So let's generate it first, and then we'll talk about it. To get a p-value here, I'm going to hit equal. I'm going to hit t dot test. And I will hit a comma. Oh, wait, I'm going to double click here, right? Yeah. Excel isn't the greatest thing ever, but it's pretty user-friendly. All right, so it's asking me for my data arrays. So I've got my untreated group. I've got my 1 through 20. Got my data set here. Looks good. I'm going to hit the comma. I'm going to highlight my treated group. That looks good too. I'm going to hit the comma. All right, so in this case, it's asking me if I want a one-tailed test or a two-tailed test. I want a one-tailed test because my null hypothesis and my alternative hypothesis indicate that I think this is going to be bigger. So I'm not looking to see if they're just different. I'm being more specific than that. I want to test if this is actually bigger than this untreated group. Is the diameter bigger in the treated group than the untreated group? And so I'm expecting it to go one way. That's what I would call a directional hypothesis. So I want the one-tailed test. Okay. So I'm going to double click that, comma. Last thing it's going to ask is what kind of t-test I want to run. We've already kind of talked about we want a two-sample t-test. And I want the one with equal variance because tomatoes all kind of grow the same way. There's no reason these two groups would have unequal variance. So I will select that one. All right, so it's got the 4 things I need. I picked the t-test function. I've got my data loaded in. I picked the number of tails I want and the type of test that I want. And I'm going to hit enter. Okay, and this gave me a p-value of 7.4% or 0.074. So that means that these observed means and standard deviations would only occur purely based on mean and standard deviation. This program is telling me that outcome would only occur 7.4% of the time if my null hypothesis was true. So in the situation where the plant food didn't work, these diameters and these means would only occur 7.4% of the time. Now that's interesting because it's bigger than my alpha level, so I'm still going to accept the null hypothesis. It's not below 5%, so I'm going to accept the null hypothesis, but it's pretty darn close. So in the real world, I might be growing some more tomatoes and collecting some more samples and seeing if my observed means continue to be different between the two groups, and then maybe if I get enough data they're different enough where it goes below this alpha level and I conclude that yeah, this is statistically significant. I have a reason to believe that this plant food works. Okay, so that's what I'm doing here. I'm comparing the p-value to the alpha level. And so the bottom line way to think about this is that if your p-value is greater than your alpha level, you are going to accept the null hypothesis. If it's lower than your alpha level, you're going to reject the null hypothesis. Okay, one other test statistic we want to grab real quick is the t-value, or the t-score, sometimes called. So we're going to hit t.inv. No, we're not going to hit equals first. So t.inv. That's the function we want. t.inv. We're going to double click. It's going to ask for a probability. So that's what a p-value is. It's the probability value. That's what it's asking for. Our p-value that we generated, I'm going to highlight. I'm going to hit a comma. It's going to ask for our degrees of freedom that we calculated. I'm going to highlight. I'm going to hit a comma. Actually, I'm not going to hit a comma because that's all we need here. It's giving me a 1.47 for the left, and because the normal curve is symmetrical, right, we know that that would be analogous to a 1.47 on the right. Because a t-value is just an expression of standard deviation, what it's saying is that on the right side of our curve, on the right side of our t-distribution, the area of 7.4% is analogous with a t-score that is 1.47% above the mean. That's all that means. So let's look at this visually, because we've got the numbers we want. We'll look at it visually. So I'm going to close out Excel. I'm going to minimize it. I'm going to maximize my photo. That'll be better. All right, so I've moved on from the Homer Simpson diagrams. I've got an actual set of curves here. So let's talk about what these mean. All right, so the way I think about t-test is that there's a theoretical distribution if your null hypothesis is true. There's a theoretical distribution if your alternative hypothesis is true. In this case, the null hypothesis is that the plant food doesn't work, that there's been no effect, and that all the means we're seeing, okay, we could give tomatoes plant food, as much as they can handle, but they still wouldn't grow any bigger. That's what this null hypothesis represents. Okay, so what happened was we got a probability value of 7.4% associated with a t-score of 1.5%, a little under 1.5%, 1.47, which is about here. So we've got a t-score that's here on our null hypothesis curve. And we've got an area under the curve that I'm highlighting with my cursor. You can imagine this being a boundary, and then the curve being a boundary, and then this bottom line being a boundary. This area, okay, is about 7.4% of the area under the curve. Okay, so that's what we just generated. That's what it looks like on our null hypothesis curve. Okay, so given that, even though it's pretty far over to the right, I'm not convinced enough that I'm going to reject the null hypothesis curve. I still think there's a chance that I could give a lot of tomatoes plant food, and all of the diameters that I measured would still fall under this null hypothesis curve. Okay. Now, suppose I got like a really tiny p-value out here that was, 2.5 standard deviations above the mean. Suppose that I had a p-value small enough that I rejected the null hypothesis and I accepted the alternative hypothesis. And so what that would mean is that I'm convinced, given the difference in my means, that if I gave all tomatoes plant food, that the mean diameter would actually be over here somewhere, that they would all be bigger, and that the distribution of tomato diameters would look something like this alternative hypothesis curve. Okay, so that's what it means when we reject a null and we accept an alternative hypothesis, that we're saying, okay, there's this theoretical alternative hypothesis that I think, reflects the situation because I think my treatment was effective. In this case, though, we're not there yet. Even though we've got a high t-score, I still think it's possible that that just happened by chance and that my plant food doesn't work and that I could give all these tomatoes plant food and they would still fall under this null hypothesis curve. Okay, that's all for now. Thanks for watching, and shoot me questions that you might have. Take care.